Hi, welcome once again to Math as a Second Language, where today we're going to discuss what I think is the topic that gives students perhaps the most difficulty with using fractions. And it's based on what we call dividing common fractions. And there's a little ditty that goes with that says ours is not to reason why, just invert and multiply. And that to me was always a big mystery. I could follow the rule, leave the first number alone, change the division sign to a times sign, and invert the second. And I could understand that, but I never understood why in a democracy you wouldn't invert both of them. Why favor one over the other? What would have happened if I was the teacher and decided to invert the first one and not the second? In essence, the easiest way out for me was to simply do what I was told. Remember, I didn't have to understand it, I just had to do the problems right. Which meant, of course, I could do them right and still have no idea as to how to use them in the real world. Now, I want to show you how any fraction problem can be reduced to an equivalent whole number problem. That's basically been our theme all along. So I want to begin with kind of an interesting thing that sometimes stumps people. Let me just cover this up for a minute. We all know, hopefully, that 6 divided by 2 is 3. How much is 6 apples divided by 2 apples? The most common answer I get is 3 apples. And amazingly enough, the answer is not 3 apples, and let's see why. What does division mean? It means what must you multiply this number by to obtain this number? What must 2 apples be multiplied by to get 6 apples as the product? Well, you have to multiply the 2 by the 3 to get 6. And how does this read now? 3 times 2 apples, it's already 6 apples. I don't need the word apples because it's already there. In other words, what this says is that in the same way that you can cancel common factors from a fraction, if the 2 units, the 2 nouns are the same, you can also cancel them. Don't confuse 6 apples divided by 2 apples with 6 apples divided by 2. See, what would this one mean? This would say, what number must you multiply by 2 to get 6 apples? And what would happen is what? Well, to get to 6, I'd have to multiply by 3, but 3 times 2 isn't 6 apples. 3 times 2 is just 6, so I'd have to put the word apples in here. And the way to remember this is, if you had 6 apples and you bundle them in groups of 2, you would get 3 groups of 2. On the other hand, if you had 6 apples and divided them equally into 2 groups, each group would have 3 apples. Okay? So the key thing, and we're going to do this in many different ways, the key thing is to remember that 6 of any unit divided by 2 of the same unit will always be 3. In other words, you can cross out the unit if it's the same in both cases. So for example, what would 6/7 divided by 2/7 be? Well, write out the word so you can see it. 6/7 divided by 2/7, the noun is the same. So the answer is 6 divided by 2, which is 3. And to see why that's logical, what's 3 times 2/7? It's 2/7 plus 2/7 plus 2/7. And when we add, we keep the common denominator and add the numerators. In other words, as small as 6/7 is, it's still 3 times the size of 2/7. Of course, if the denominators aren't the same, see here we can't do this because the 3 and the 2 are modifying different nouns. What we do in that case is we simply replace each fraction by equivalent fractions that have the same denominator. And how do we do that? If this denominator is 5 and this denominator is 7, a common denominator will always be 5 times 7. And so what you can do over here is, starting with 3/5, multiply numerator and denominator by 7. Here, starting with 2/7, multiply numerator and denominator by 5. And now the problem becomes what? 21/35 divided by 10/35. Now are the denominators the same? Yep. Therefore, can I cross them out, pretend they're not there? So the answer is what? The quotient of the two numerators, 21/10. Okay. Notice I did not say invert and multiply, but what would have happened if I did? Suppose I took the mechanical rule, ours is not to reason why, just invert and multiply. The first number would stay the same. The division sign would become a times sign. I would invert the second one. That means take the reciprocal. And the problem would be 3/5 times 7/2. So I multiply across. By the way, let me make a little aside here. If you're studying European literature and you have trouble with French literature, you can wait till that chapter is over and never have to see it again. In other words, you can study German literature, Spanish literature. You don't have to see French literature again. In math, it's ongoing. You can't say, oh, we had multiplication last time, I can forget it now, I passed the test on it. No, it's going to come up over and over and over. So, for example, in this particular problem over here, once I use the invert and multiply rule, I'm assuming that you still remember the rule for multiplication, and we do get the same answer. And what is the test to see that the answer we got is correct? See, it's easy to say invert and multiply, but what is the real test to see if this is correct? When you divide two numbers, 3/5 divided by 2/7, the correct answer is the number you have to multiply 2/7 by to get 3/5. Let's see what happens if we take 2/7 and multiply that by 21/10. 7 goes into 21 3 times. 2 goes into 10 5 times. And the answer is 3 times 1 over 5 times 1, which is 3/5. And that's the correct answer, okay? What about our friend the cornbread? Do you think we could use the cornbread to do the problem the same way? Well, I wouldn't bring it up if you couldn't, so I guess we can. Let's go see what happens. What are we going to be doing? We're going to be dividing 3/5 by 2/7, but now we're going to use the cornbread. How many pieces should the cornbread be sliced into? 5 times 7 is 35. So we're now going to assume that the cornbread has 35 pieces. So 3/5 of the cornbread would be 3/5 of 35 pieces. 35 divided by 5 is 7. 7 times 3 is 21. So 3/5 of the cornbread is 21 pieces. 2/7 of the cornbread is 2/7 of 35 pieces. 35 divided by 7 is 5. 5 times 2 is 10. So 3/5 of the cornbread is 21 pieces. 2/7 of the cornbread is 10 pieces. So if I'm going to divide 3/5 of the cornbread by 2/7 of the cornbread, I'm dividing 21 pieces by 10 pieces. The pieces are the common noun. We can cross those out. And so the answer is going to be what? 21 divided by 10. And again, as I said before, you can mechanically invert and multiply. And by the way, students will say to me, isn't invert and multiply easier than the way you do it? And what do you think my answer is? I invert and multiply when I divide. The difference is I understand why it works. And when I understand why it works, as I'll show you in a little while, I can solve word problems better that way, instead of just trying to write down arbitrarily number and hope that they work out right. So once and for all, let's look at the logic behind invert and multiply. I'm going to need two properties of multiplication to show you why this works, and I don't think it's hard to follow. The first one is if you multiply a common fraction by 1, it doesn't change the value of the fraction. So if you have 3/5, what's another way of multiplying by 1? It's 1 over 1. You multiply across, you get 3/5. And if you want to use the of interpretation, 3/5 of the cornbread is 3/5 of the cornbread. 3/5 of one cornbread is 3/5 of a cornbread. So is that one pretty easy? Okay, if you multiply a fraction by 1, you don't change its value. The second one says, if we take any fraction, I'll write it as n over d, numerator over denominator, and multiply it by its reciprocal, that's d over n, you invert the numerator, reverse the numerator and denominator, the product will always be 1. Why is that? Because you multiply across, you get n times d over d times n. Multiplication is commutative, so the numerator equals the denominator, and if the numerator equals the denominator, the answer is always 1. And to see that more clearly, if you have something like 6 over 6, what does this mean? It's 6 divided by 6. It says, what must you multiply 6 by to get 6? And obviously, you multiply 6 by 1 to keep the answer 6. So is that clear now? If I multiply a fraction by 1, it's not going to change. And if I multiply a fraction by its reciprocal, I'll always get 1. Now, why do you think that's important? When I want to multiply by something to get a certain answer, isn't the easiest number to multiply by is 1? That's what I want to use here. So let me show you how the invert and multiply rule came about. What does 3/5 divided by 7 equal parentheses mean? It means what number do you have to put into the parentheses such that when you multiply it by 2/7, the answer will be 3/5. Okay? Wouldn't this problem have been much easier if there was a 1 over here? What must you multiply 1 by to get 3/5? The answer would be 3/5, wouldn't it? Problem is there isn't a 1 over here, but I do have a technique that converts that into 1. Any fraction times its reciprocal is 1. So what I'm going to do over here is multiply by 7 over 2. 7 over 2 times 2 over 7. And can you see how it cancels? Gives me 1. Now what do I have to multiply 1 by to get 3/5? 1 times what is 3/5? Well, 1 times 3/5. Notice that I never said invert and multiply. I worked this problem out logically. I said, well, to get from 2/7 to 3/5, I'll first multiply by 7/2. That will bring me to 1. Then I'll multiply the 1 by 3/5. Then I can become arrogant and say, well, you guys would never understand this, so let me give you a mechanical recipe to use. Look at the problem and look at the answer and see what's happened. 3/5 started the problem. The 3/5 is still there. So the first step is leave the first number alone. There was a division sign here. There's a times sign here. So the second step is to say, change the division sign to a times sign. The second number doesn't appear over here, but what does appear? It's reciprocal. It's inverse. So you say, okay, leave the first number alone, change the division to a times, and invert the second one. And lo and behold, there's your answer. Let's just try it with one problem. What's 4/9 divided by 5/13? If I use the mechanical recipe, I leave the 4/9 alone, I change the division to a times sign, right? And invert the second one. So I get 4/9 times 13/5, and so the answer would be 52/45, I guess. And by the way, I can check that, because if this is right, what should happen? If I multiply 52/45 by 5/13, I should get 4/9, shouldn't I? 13 goes into 52 4 times. 5 goes into 45 9 times. 4 times 1 is 4. 9 times 1 is 9. And it works. And you see, I'm not going to take the time to do this, but if you inverted both of them, which is certainly permissible, it just won't be the right answer. If you inverted the left-hand number and left the right-hand one alone, again you could do that, it just wouldn't be the right answer. Let's see what the logic was here. I want to get, by multiplication, from 5/13 to 4/9, so I'm going to do it in 2 steps. I'll first multiply by 13/5 to get the answer to be 1. Then I'll multiply 1 by 4/9 to get 4/9. What have I done altogether? I've multiplied 13/5 by 4/9. Okay? Some math books do something more abstractly, which we can talk about a little bit. Some math people prefer to write any division problem as a fraction. See, this is not a common fraction, even though I write it as A over B over C over D, and I just made a double line here to make this thing easier to read. See, to be a common fraction, it's not just the quotient of two numbers, it has to be the quotient of two whole numbers. But the important point is that the same rules that apply to ratios, to division problems, when you're working with whole numbers, also applies to fractions as well. In other words, even for a fractional problem, if you multiply numerator and denominator by the same number, you don't change the value. So if we write a over b divided by c over d as a over b over c over d, the easiest denominator we like from a computational point of view is 1. What can I multiply c over d by to get 1? I'll just multiply it by its reciprocal. But if I multiply the denominator by 1, I also have to multiply, if I multiply the denominator by something, I have to multiply the numerator by the same number. So this becomes what? A over b times d over c. And what does this become? This becomes 1. And if the denominator is 1, you can ignore it. And this says that ab divided by cd is the same as ab times d over c. Okay? And again, this sounds strange to a lot of students because we've been taught that multiplying should make things bigger and dividing makes them smaller, which is certainly true when you're dealing with whole numbers. But when you're dealing with fractions, you have to understand the concept. Why can 1/2 times 1/3 is 1/6? It's clear by looking that 1/6 of a cornbread is less than either 1/2 of the cornbread or 1/3 of the cornbread. Okay? So the answer could become smaller. And why was that? Because you're taking a fractional part of a fractional part. You're taking 1/2 of the 1/3. Now you take 1/10 divided by 1/100th. To the naked eye, if I can use the word naked here, the answer should somehow be very small because look at how small 1/10 is and how small 1/100th is. Let me use the mechanical rule. I leave the 1/10 alone, change the division to a time sign, and invert the second number, and I have 1 over 10 times 1 over 100, and if I cancel everything out, the answer is 10. How can I divide two such small numbers and get an answer that's way out of proportion to these numbers? And the answer is that when you divide two numbers, you're finding their relative size. What this answer says is that 1/10 is talking to 1/100th, and he says to him, you know, I may be small, but I'm still 10 times bigger than you. Isn't that true? If you start with 1/100th and multiply that by 10, okay, the answer is now 1/10. You ever see the automobile bumper sticker, the rear bumper sticker? I think it's humorous. It says, I may be slow, but I'm still ahead of you. So when you say 12 divided by 4 is 3, it's as if 12 is saying, I may not be very big, but I'm 3 times as big as you. Okay? The quotient of two numbers tells us the size of one number relative to the size of the second number. At any rate, all my purpose was to show you how division of fractions can be translated into a whole number problem. I'll emphasize that more in terms of our practice problem. Remember what our practice problem is. You pause the video, do the problem, and then resume the video. And so let me tell you what our problem is today. It says an object is traveling at a constant speed. If it travels 2/3 of a mile in 4/5 of a minute, what is its speed in miles per hour? And can you see people having fraction anxiety with this? I mean, what's 2/3 of a mile? What's 4/5 of a minute? I don't know how to do this problem. Well, what I want you to see is, after you come back, take a break. Miles per minute means miles divided by minutes. So you have 2/3 of a mile divided by 4/5 of a minute. Now, how do you divide? You divide the two adjectives, 2/4 and 4/5, so it's 2/4 divided by 4/5, and the label is going to be what? Miles per minute. So you're going 2/3 divided by 4/5 miles per minute. If we mechanically invoke the invert and multiply rule, This becomes 2/3 times 5/4 miles per minute. This is the same as 10/12, which I guess you could have reduced to 5/6, but I'm not going to bother doing that. That's each minute. How many minutes are there in an hour? 60, so you're going to go 10/12 of a mile 60 times. 12 goes into 60 5 times, and so your speed is 50 miles per hour. Pretty straightforward if you're not afraid of dealing with fractions. And even if you're not afraid of dealing with fractions, you might wonder why this technique still works. So I thought I would show this to you in a way that's more verbal. 2/3 miles per 4/5 of a minute means what? Every time you go 2/3 of a mile, it will take 4/5 of a minute. Well, how would I get rid of denominators here? There's a 3 and a 5. Don't they both go into 15? So I say, okay, if this goes 2/3 of a mile every 4/5 of a minute, if I go 4/5 of a minute 15 times, I'll also go 2/3 of a mile 15 times. Well, 3 goes into 15 5 times. 5 times 2 is 10. 5 goes into 15 3 times. 3 times 4 is 12. So in other words, the scary rate, 2/3 of a mile per 4/5 of a minute, translate very nicely into 10 miles per 12 minutes. And you can do this with any numbers. It doesn't matter how messy it is. Suppose it was 2/7 miles per 3/13 of a minute. 7 times 13 is 91. So you multiply both of these numbers by 91, okay? Saying that if I go 3/13 of a minute 91 times, I'll go 2/7 of a mile 91 times. So you just multiply both rates by 19. 7 goes into 91 13 times. 13 times 2 is 26. 13 goes into 91 7 times. 7 times 3 is 21. So this rather scary ratio, 2/7 of a mile per 3/13 minutes, is just another way of saying you went 26 miles every 21 minutes. And somehow you don't panic when you say, I went 26 miles in 21 minutes. You might wonder why you'd want to know the answer, but it's not that hard to get the answer. Well, that brings us to the conclusion of today's lesson, and I will look forward to seeing you all next time. Stay well, have fun, study hard.